Hello, this is John Hearn again for part 2 of hydroelectric power. And as I mentioned in the last lecture, here we're going to be looking at the environmental impact of hydroelectric power. So first, just by way of review from the last lecture, we looked at a little bit of the history of hydropower. We noticed first that hydroelectric power, its primary source is solar energy. So recall that there are three primary sources of power: solar energy, the rotation of the Earth, and the heat from the Earth's core. So hydroelectric power gets its energy from the water cycle. It dates back to antiquity, so these water wheels have been used since ancient times, and it's in recent years that the turbine has revolutionized hydropower. So the first turbine was invented in the sort of early 1800s, and this is really when hydropower took off for powering the Industrial Revolution in a lot of cities. There are two types of turbines. There were impulse turbines. These require high head pressure. The high head pressure is required to get the velocity and therefore momentum of the water high enough to either move paddles or something that's capturing that energy. And then there's also reaction turbines. Reaction turbines require a high flow rate, and so you get as the water moves past blades like fan blades, they cause a rotation. And so all of these methods are designed to take power energy from water and turn it into shaft work. Okay, so we also noticed last time that reservoir-based hydropower is already stored energy. So in other words, we don't have to rely on waiting for it to rain for us to have hydropower. We store up hydropower behind dams, and then we can release it when needed so that it can match demand. And this really sets hydroelectric power apart from some of the other renewable energy sources, because you either need to store that energy so that you can use it later, or you need to just use it when you make it, right? So if the sun's not shining, you don't get solar energy. And so hydroelectric power is a natural way to store that energy without having to add any more technological strategies. Okay, so the book, let me read this little excerpt from the book. Compared to other power generation methods, there are numerous benefits of hydropower, such as low production cost, no emission of CO2 and other harmful gases, flood control, land irrigation, and water navigation. So the phrase that I want to really zero in on here is no emission of CO2. I read that, and I thought of this nice quote from one of my favorite movies, The Princess Bride. "We are men of action. Lies do not become us." And a cursory internet search reveals that greenhouse gas emissions are a potentially huge problem from dams in the United States and elsewhere. Now, to be fair, the authors do later on mention this. They said, in the absence of a water reservoir formed by a dam, the biomass would decompose anaerobically into CO2, but when covered by water, it decomposes anaerobically, producing methane gas, which is 30 times more potent as a greenhouse gas than CO2. So they acknowledge this, but it almost feels like a footnote. Okay, so in today's lecture, we're going to actually take a look at this and see, how big of a problem might this be. Okay, so in the article that I cited there, and this is the the link down here. Of course, you probably have to just type that in, but that link will get you to this article. And they looked at life cycle greenhouse gas emissions. A lot of renewable energy, especially in the sort of media and other sort of communication, only focus on the greenhouse gas emissions or environmental impact while it's producing power. For example, you got wind and solar. Well, those are capturing energy from the wind, energy from the sun, and they're not producing any greenhouse gas emissions. However, they do require greenhouse gas emissions for their installation or their maintenance or other aspects of delivering that power to the customer. And so for hydropower, that's these, let me see if this, that's over here. We've got hydropower here. And the hydropower has a very wide range of life cycle greenhouse gas emissions. So over here on the y-axis, let's just take a look at that. The y-axis is grams of CO2 equivalent per kilowatt hour. Okay, so this is not just CO2, it's greenhouse gas emissions. So as that excerpt from the book mentioned, methane is included in that, which is a very potent greenhouse gas. And you can see here that hydroelectric power is either, in the case of these river and stream hydroelectric systems, they're better than everything. But we've got these, reservoir-based ones that can be pretty bad. So we're going to sort of unpack this a little bit and see where the uncertainties are, what we can say for sure, and we'll take a look at that. So this is an excerpt from that book, and it says, similarly, Fernside compared the hydropower generated from the Petite Saut Dam, which is in French Guiana, with electricity generated from combined cycle natural gas, and found that the greenhouse gas emission from the dam are 19 times higher than the natural gas-based electricity. And so this is some data that was collected and from 2015, where greenhouse gas emissions are worse than natural gas-based electricity, 19 times worse, which probably means it's worse than coal-fired power plants, which is considered the dirtiest way to make electricity. So this is definitely not a closed case. So let's take a look. Now, we're going to take a look at the bottom first. The greenhouse gas emissions of dams are highly variable, and part of the reason for that is because of the various pieces that go into the equation. So one of those pieces is the construction. So here we've got just 4 different types of dams: embankment, arch, gravity, and buttress dams. And each one of these dam types have different materials, right? And so here I've got a little bit of just 2 bullet points for embankment dams. So embankment dams require more material than the other dams, but that material is mainly just sand, rock, and clay. So this is just stuff you dig out of the earth. And so the embankment dams are 46% raw material greenhouse gas emissions of the gravity dam, right? So even though embankment dams require more material, they actually have fewer greenhouse gas emissions than, say, a gravity dam, and that's just because the gravity dam requires so much more concrete. So how do all these different pieces affect the greenhouse gas emissions? So here you can see 5 sort of basic categories of materials that go into constructing dams: steel, cement, polyvinyl chloride, sand, gravel, and rock. Okay, and what I want to bring your attention to is this last column over here, which is the average greenhouse gas emissions. So this is kilograms of CO2 equivalent per megawatt hour. So this is essentially the life cycle cost of CO2 emissions based on what the anticipated energy production would be for that dam. And so you can see down at the bottom, sand, gravel, and rock have very little greenhouse gas emission. That's because it's just dug out of the earth. There's no fabrication needed as there is with, say, cement and steel, where you have to either smelt iron and iron ore to make steel, or in the case of cement, you have to heat up calcium carbonate, which releases carbon dioxide into the atmosphere, and you had to burn something to do that. So cement has a pretty high contribution to CO2 emissions, and those are the highest. So cement has an average greenhouse gas emission of 7.1, and PVC is 5.1. PVC is used in the penstock, so this is for delivering the water to the turbines. Okay, but if you look, the construction part of this equation is actually almost down there in the noise. It's the little yellow box at the bottom of these graphs. So the construction greenhouse gas emissions aren't really a problem. So let's look at demolition. Demolition looks like it could be pretty big. So it's the little sort of brown hash marks there that are circled. And for some types of dams, this is the primary contributor to their greenhouse gas emissions. So the greenhouse gas emissions from dam removal are wild guesses. Okay, so first, I'd like to point out there's no data or studies of large dam removal. Almost all the dams in the United States that were removed only had a 4-meter height. So these are very small dams, and so the data that we do have is just based on small dam removal, which is really going to skew the results and probably give us some kind of systematic error in our estimations. So we can just at least guess what might contribute to greenhouse gas emissions. And so some of those different pieces, first, demolition machines and transportation of debris. So this is essentially you bring in your bulldozers, whatever stuff you need to tear down the dam, and you have to haul that off to a landfill, right? Or wherever its final resting place is. So all that's going to cost some energy, and that energy is going to emit some greenhouse gas emissions, energy consumption. So, and then the other is decomposition of organic sediments, which this piece of it could be enormous. So that first piece I mentioned might actually be negligible. I mean, just in the noise, sort of like the greenhouse gas emissions from the dam construction. So here, the decomposition of organic sediments might be a really big factor. So there's a range here from 35 to 380 grams of carbon dioxide equivalent per kilowatt hour. So this is, like I said, this is a wild guess. This is an order of magnitude. On the high end, around 400, this is getting close to the life cycle greenhouse gas emissions of natural gas plants, right? Which have 500 grams of CO2 per kilowatt hour. So, but on the low end, it's not a big contributor, right? So this is a question that really needs to be answered. What are the greenhouse gas emissions for dam removal? Okay, so the next biggest thing, and actually the biggest for this, the reservoir in the tropical region is reservoir greenhouse gas emissions. So this green part of these bar graphs are the reservoir greenhouse gas emissions. And here you can see that it's huge for this one with the little subscript TR. The TR stands for tropical, okay? So these are reservoirs that are installed in tropical climates, all right? So these are the three different climates. We've got boreal, temperate, and tropical. And can they really be that big? That's huge. That's worse than the demolition. So let's take a look. So in the absence of a water reservoir formed by the dam, the biomass would decompose aerobically into CO2 when covered by water. It decomposes anaerobically. So this is that same excerpt that I read earlier, producing methane gas, which is 30 times more potent as a greenhouse gas. So this is really the mechanism by which reservoir greenhouse gas emissions can be so bad, all right? And in a tropical region, you're talking about more organic matter decomposing anaerobically than you are in a temperate or boreal climate. And that's really the main contributor. So it depends on where the reservoir is located. But because of that factor of 30, that can really skew this part of the calculation to an enormous greenhouse gas emission equivalent. So here's a little bit of data for reservoir greenhouse gas emissions. So here you can see the three climate zones, boreal, temperate, and tropical. And then you can see the reservoir greenhouse gas emission rate, which is for tropical is 2,733 compared to the other two, which are 550 and 870. And in the United States, this isn't a huge problem simply because we don't have that much tropical climate. So the actual greenhouse gas emissions from tropical reservoirs in the United States isn't that much. But in other areas in the world, if we're talking about building dams in Brazil or parts of Africa, then you could have huge greenhouse gas emissions from the methane and other gases that are produced from these reservoirs. And it gets even worse for pumped hydropower systems. Okay, so a pumped hydropower system isn't really hydroelectric power. Okay, so let's distinguish hydroelectric power from this. Hydroelectric power, we're using energy from rain that has fallen on higher elevations, and as that water flows down to lower elevations, we're going to grab some of that potential energy and turn it into whatever kind of useful work we want to do, right? And so that's a hydroelectric system or a hydropower system. But pumped hydropower systems are not generating power, they are storing power. Okay, so for example, Raccoon Mountain over near Chattanooga, they take excess electrical power that's produced from the nuclear power plants, and in low demand times, they'll pump water up to a reservoir, and then at high demand times, they release water to generate power to help meet demand. And so this is essentially an energy storage technology. Okay, and I think there's a whole nother chapter on these pumped hydropower systems, but it was part of this. I just want to point out here that for the pumped hydropower systems, they have a much higher operation and maintenance contribution to their greenhouse gas emissions. So that's the sort of dark blue region right in here. Okay, so this is the operation and maintenance greenhouse gas emissions, which arise because not everything's 100% efficient. So as the water is pumped up, you lose some energy in the pumps, in the engines that are, or the motors that are driving those pumps as they let off heat. Now, I will say that if the pumped hydropower system is being used to store energy from another renewable source, for example, solar energy, then I'm sure that would adjust or affect these operation and maintenance emissions. But that's the main difference between the pumped hydropower systems. You actually have to pump the water up before you can use it, and so there's some energy loss there. Okay, so there's another type of hydropower system, and this is a diversion system. So essentially you take water from a river and you divert it to a powerhouse. Okay. Now this requires that there's a natural slope in the river that's steep enough so that you get enough head pressure to run your turbines. And a dam is not needed, although we'll see an example here in a minute where there is a dam used. And it's typically done on a smaller scale than some of these larger reservoir-based hydroelectric systems. But the advantage here is that they have smaller impacts on river flow. And that's because you're not damming up a huge reservoir, which affects tributaries and everything upstream. And then you're also not releasing necessarily lots of water all at once. So you get these sort of surges of water downstream. You're essentially just taking the water and you're putting it through a turbine on its way down the river. Now, there would be a section of river, and I'll just point this out, a section of river, like this section right here, that does have reduced water flow because you have diverted it. Now, it just depends on the scale of your system, what kind of environmental impact that would have. Okay, so the book kind of mentioned these sort of micro hydropower systems, and that got me wondering, how much energy can we capture off of a house roof? So just to kind of see, okay, can I install one of these things, it's some kind of hydropower system on my gutters and charge some batteries and, get off the grid? Let's see. So, essentially, I'm going to throw in some numbers here. We got a surface area of the roof of 1,500 square feet. So this is sort of a probably average size house in our area. The annual rainfall in sort of the Chattanooga and Cleveland areas here in southeast Tennessee is 51 inches. And then we're just going to take a vertical drop of 3 meters. This is a little ambitious, but we'll do it nonetheless. Okay, and then we'll say that our efficiency is 80%. Okay, so we'll just do that. So essentially, what we got to do is first calculate the volume of water that we can that we're collecting. Okay, so we've got 51 inches of rainfall. We've got multiply that by the area of the roof, which is 1,500 square feet, and then we just take care of our units. Okay, so we've got to convert everything. We're going to convert everything into meters, and we get 182 cubic meters. So that's how much water we could collect off of an average size household roof. And then if we throw that into our energy equation, which we looked at in the last lecture, This is the energy is the efficiency, which is eta, times the mass of water, and in this case that's rho v, the density times the volume, times g times h, where h is the vertical drop. So then we get 4.3 megajoules, and we can convert that into kilowatt hours. It's 1.2 kilowatt hours. This is only 0.1% of our monthly need. So, will this work? I'm afraid not. Okay, so what are the other impacts of reservoir hydropower? So let's go back to this, because really we've focused on, so far, just greenhouse gas emissions. And while that's, all the rage these days, it's not the whole story, right? So we need to not just think about greenhouse gas emissions, we need to think about environmental impact. And not just environmental impact, human impact, right? So what are the other impacts of reservoir hydropower? And so I'm going to take you through a few pieces of data for the Three Gorges Dam, which was built on the Yangtze River in China. Okay, and so this was, I've got some data here. But this is upstream from Shanghai. So over here on the right, you've got Shanghai. And then this is the Yangtze River here. And so the dam that we're going to be looking at is right here. So we'll look at its environmental impact. Okay, so first, the dam was constructed over many years, and it was fully operational, I think, in like 2009 was when it was filled to capacity. So it took several years to get to fill up. But you can see here, this is from the U.S. Geologic Survey. In 1993, this is the region, right, that we're looking at of the river. And in 2013, you can see what it looks like. Okay, this is the Three Gorges Dam. So it backed up a lot of the river. You can see that the Chinese cut some canals out through here for diverting water, and this is the dam right here. And this is the reservoir up here. So the reservoir is up here, and it made a huge reservoir. This is the largest hydroelectric power dam in the world. So what are these other impacts? First of all, 1.25 million people were displaced. Okay, now these pictures that I've got here are from a little cruise that my wife went on back in, let's see, what year was that? That was 19, I'm dating myself. No, it wasn't. No, it was 2000. This was 2000. I'm still dating myself. But this is before I was married, so she went to China for a summer, and she was in Wuhan, which was a city just downstream of where they were building the dam. So the dam was under construction. Anyways, you can see here some of the pictures. I took these out of her scrapbook. But there were a lot of people that their livelihood was right along the river, and 1.25 million of them were displaced. They had to move to other cities, and that's a pretty big impact. You can also see some of the gorge and some of the scenery here in some of the pictures that my wife took. She was among the last people over the next few years the reservoir filled up to actually see some of these things with their own eyes. Okay, so 1.25 million people were displaced. The mean air temperature increased by 0.2 to 1 degree Celsius. Okay, so this is just in the reservoir area. So this, we're not talking about global, temperature. We're talking about in the reservoir area, the mean air temperature increased. Precipitation increased from 2 to 9%. right? Now, these are just environmental impacts. These are changes in the environment. Now, you might argue whether or not these are good or not. Yeah, more rain might be good. A higher temperature might be good, but these are nevertheless changes that are happening because of the dam. Algal blooms increased, and so you can see the data here from 2003, which is when the dam was completed. I think it was completed in 2003, and then they started filling it. And you can see here that the frequency of algal blooms went up as the reservoir was filling. And so this has all kinds of other consequences for water quality and the health of people who rely on the water for their livelihoods. And this actually caught me off guard. When I read this, I was like, oh, but it makes sense. The earthquake frequency increased. Okay, so here, this data here shows you the earthquakes from 1996 through 2009. 2009 was when the reservoir was completely filled, was full, and 2003 was when they started filling it, I think. And you can see here from 96 through 2002, you can see that most years had earthquake frequencies of maybe 40 to 60, 90, something like that. 96 had 173. But anyways, you can look down at the bottom of this, and you see down here, right here, the average annual earthquake frequency from 1959 through 2003 was 28.5. All right, and then you can just see in this chart, you've got over 1,000 earthquakes in many of these years, 2000 and 2008. And so the average annual from 2003 to 2009 is 1,290, well, 1,287.7. But this is a huge increase in earthquakes. Now, the reason for this is because you're essentially piling on all this water where there wasn't any, and the hydrostatic pressure that is generated below the reservoir can cause cracks and stuff in the rocks beneath it, which can cause earthquakes. And so this is something that is apparently well known, and I think probably geologists are probably a little more familiar with this phenomenon. But I was surprised by this. I wasn't expecting earthquake frequency, but this is a pretty big effect of this dam. Now, this is, like I said, the biggest dam in the world for generating hydroelectric power. It's a very large dam, and so the reservoir is quite a bit deeper than probably most reservoirs you will find elsewhere. Okay, so in addition to that, we've got in our own backyard, we have dams all over the place. Okay, so the TVA, FDR in part of his New Deal built a whole bunch of infrastructure down here in the Tennessee Valley, and they built a whole bunch of hydroelectric dams. And some of those are over here along the Ocoee River, 3 of them. And I want to just take a look at these 3 and just give you a few details about those. But this is in my backyard. I live up here in Cleveland, Tennessee. And so the Ocoee River is literally just in my backyard. So the 3 dams are Ocoee number 1, 2, and 3. Ocoee number 1 is located at the base of what's called Parksville Lake. And Ocoee number 1 was built in 1911, it's been in service since 1911, and it generates 24 megawatts of power. And this is a picture of it here, and it's just a traditional, reservoir hydroelectric power generator. Ocoee number 2, I think, is kind of interesting. If you've ever rafted the Ocoee River, you put in just below this dam. Now, right now, this picture right here, so this Ocoee number 2 is 23 megawatts, and it was in operation since 1913. Now here, you'll see right here, there's no water flowing over this. The water's no water's flowing in here at all. But this is where you actually put in for rafting the middle Ocoee. You come in down here and you put in right there when the water's flowing. But this is a diversion dam. Okay, so here over here in this section right here, there's 2 spots here. There's one spot where the water comes through for rafting and such, and then the other is this spot right here, and this is a diversion. Okay, so they take water that would be flowing downriver and they send it through here to a powerhouse. And so I mentioned the diversion dams, and this is one of those. And when they're running the water through this flume, it really dries up the riverbed, and so this has wreaked havoc on the Ocoee River. I've got a friend here at Lee who studies wildlife, and he said that these dams have just killed the Ocoee River, and there's nothing in them. But then we have Ocoee number 3. It's near the almost at Ducktown. And this is Ocoee number 3. It generates 29 megawatts, and it's been in service since 1942. Now there's other hydroelectric dams in our area, but I thought those 3 are ones that I've actually physically been to, or I've actually rafted the Ocoee, so I've seen some of these. And if you have a chance, you should go up later this spring when it's nice out and take a look at the Ocoee River. All right, I was reviewing the video. I noticed that for some reason it didn't capture this last slide, so I just want to end with this quick question. What are the life cycle environmental impacts of hydroelectric power? And I really need more research to answer this question. So anyway, that'll do it. I look forward to seeing your lectures later this semester.